Okay, so let's do that. I'm going to write another loop on top of this loop. So what are the n's you want me to run? So I'm going to, instead of setting n to something, I'm going to say for n, well, I don't think I can do that in MATLAB, but let me just take my n list to be a list of n's. I think we started with 50, right? 100, 200, 400, well, let's do 500 and 1,000, 2,000, 5,000, 10,000. Oh, let's stop over here. Okay, and for in goes from 1 to the length of n list. Okay, let me set n equal to n list in. Okay, then everything else follows. In the end, I'm going to assess what I get. So I'm going to also make a result list. It's going to be empty in the beginning, and every time we run for the Euler, we'll say result list is equal to result list, and I'm going to append something that is a u next, which is the u at the very end of the time integration, +1, right? And I'm going to end and see what the result is. So let me clear up everything and run this again. Well, let me see my result list. Okay, let me actually open this result list for us to be able to see what we get. We can see that as we increase the number of time steps, what do we see here? Result get closer and closer to 0, right? And in particular, as I increase n, I mean that's important because it relates to your homework, right? The same kind of thing we want to say in our homework is how do we quantify, right, the behavior of the error as n increases?
It scales the error, scales the same way that the n increases. So for like each power of n, the error is also decreasing that power.
Okay, so you're saying for every increase of n, this decreases, right, by some factor. So why don't we plot them? So let's actually plot n list and the result list. Okay. Well, let's plot it as symbols and see what we get. Okay. Of course, we have imaginary part, so we are just plotting the real part. But in order to quantify the magnitude, why don't we just plot this with the absolute value, which is for imaginary numbers that plots the magnitude, right? Okay, so we get this. Well, what does that look like for you? We can see as n increases, the error decreases, right? But it's very hard to see, especially at the right-hand side when the error gets very small, gets very close to 0. It's very hard to quantify. Anybody have any suggestion of how to plot it differently so that we can see better? Log scale, right? I mean, when things are scattered over a huge range in terms of order of magnitude, which is this case, right? Plotting log scale is actually much better. And in this case, we have both the x-axis, which is n, and y-axis, the error. They are both spanning like about 2 orders of magnitude, right? So plotting both in terms of log is actually the preferred approach. What do we get? Let's actually plot it in with a line, okay? And let's make a grid. All right, what do you see here? Straight line, right? What slope is it? What is this? -1, right? So when you see a slope of -1 in a log-log plot, what does that tell you? exponential decay? Well, if you see a straight line in a semi-log plot, right? If I plot this as in a linear scale and this in log scale, I see this. That is exponential decay. When I plot both axes as log and I see a straight line is not exponential decay, right? If this is linear, then it's exponential decay because every time I step over a fixed interval, I see this drop in a fixed order of magnitude. That's exponential decay. But here's not. When I go towards the right over a fixed interval, I'm actually multiplying the axis by a fixed number, right? So if I multiply x by a fixed number, the y is also multiplied by a fixed number. What is that trend? It's a polynomial, right? Some power, right? Actually, this case is actually that power is -1. So the y-axis is exactly inversely proportional to the x-axis, right? Every time, if the slope is -1, every time I multiply the x-axis by 10, the y-axis gets divided by 10. That's a slope of -1. Just to get your mind to work a little bit harder, if the slope were -2, what does that mean? Right, every time I multiply x by a factor of 10, y gets divided by a factor of 100 if the slope is -2, right? That means y is x to the power of -2, right? Because, yeah, 10 to the power of -2 is going to be 1/100. And if the slope is -3, it's y to the x of -3. If the slope is -half, right, we are going to have y is equal to 1/square root of x, right? So this is what this kind of a log-log plot is going to give you. You're going to see a lot of these log-log plots in this class because a lot of the schemes we're going to study, the accuracy of the scheme is going to be a certain polynomial, a certain power of the discretization expense, let's say, right here. Basically, n is how much work we put into evaluating this formula, right? Every time step, the work is fixed. If you increase n, we are basically doing the same thing n times. If n is 10,000, the expense is going to be 10 times that of when the time step is 1,000, all right?